We've been talking a lot in this module about interconnecting switches. We said that we could interconnect switches with a trunk, and that trunk can carry traffic for multiple VLANs. We talked about VTP that would allow us to create a VLAN or delete or modify a VLAN on one switch and have that change propagated over the trunk to another switch. Well, if we're interconnecting switches like that, and if we're sending traffic for multiple VLANs between switches over a connection, wouldn't it be great if that connection had extra bandwidth, maybe more bandwidth than one of our typical switch ports? Well, that's what Ether Channel can do for us. Ether Channel can allow us to logically bundle together multiple ports into one logical interface. On screen, you see that these switches are interconnected with a couple of ports, and if we logically bundle those ports together, we can create an Ether channel that gives us higher bandwidth between those switches. We can get some load balancing. Sometimes packets or frames will use one port, sometimes packets or frames will use the other port, and if one of those ports goes down, that doesn't mean the Ether channel goes down. No, we have some redundancy here. If we lose a port, then we can continue to send traffic between those switches. The way load balancing works, however, is often misunderstood. Let's talk a bit more about how load balancing really works with Ether channel. Many times when people are first introduced to Ether channel, they visualize something like this. They imagine that maybe we've got a server farm hanging off of switch B, and I've got 4 physical connections, 4 fast Ethernet connections perhaps, between switches A and B. Well, the thought might be when I'm sending traffic to these different servers, I'm going to be load balancing. I'm going to be using different physical paths between switches A and B. However, it depends. It depends on the load balancing algorithm that we're using. So let's say that we've got an Ether channel created. We've bundled these 4 physical connections together. What options do we have for load balancing? One option is based on the destination IP address. The switch can look at the destination IP address and look at the last 2 bits or the last 3 bits if we have 8 physical connections to determine what path is going to be taken. We could make our decision based on a destination MAC address, but instead of having a decision made on just the destination or just the source, I prefer to mix it up a little bit. I like to combine both source and destination and look at the source and destination IP addresses or the source and destination MAC addresses. What happens is the switch will perform a Boolean operation. It will do an exclusive OR between the last bits in the source and destination MAC addresses or source and destination IP addresses. And the result of that exclusive OR operation determines which physical path is going to be used. And just like we could use a destination IP address or a destination MAC address, we could look at just the source IP or just the source MAC address. Let's take a look at an example though. Let's say that these 3 servers have MAC addresses that end in a 1 for the first server. The last hexadecimal digit for the MAC address for the second server is a 5, and the last hexadecimal digit for the last server is a D. Well, those seem different enough, but if we break the hexadecimal digits down into binary, as I've done for you in that table on screen, take a look at the last 2 bits. The last 2 bits of all of those hexadecimal digits are 0, 1. And we have 4 physical paths between these switches. How many binary digits do we need to represent 4 different paths? We just need 2. 2 bits give us 4 possible combinations, and I've labeled these for you on screen. We've got a path that can be used when our load balancing algorithm generates a 0, 0. I've got another path for 0, 1, another path for 1, 0, and another path for 1, 1. Well, in this case, if we're using just the destination MAC address, and we're sending traffic to these 3 different servers, well, the last 2 bits in their MAC address, in their 48-bit MAC addresses, just looking at the last 2 bits, they're equal. They're 0, 1. That means that that second link from the top that I have labeled with a 0, 1, that's the link that's going to be used when we're sending traffic to each of those servers. PC1 sends traffic to each of those servers, and as we're going between switches A and B, we're using that same link, regardless of server destination, because they end in the same 2 bits. If we look at their MAC addresses. That's the reason I like to, as I said, mix it up a little bit and do an exclusive OR operation with either the IP addresses or the MAC addresses. And when we're setting up this Ether channel, we can go in and just tell each side that our Ether channel is in the on state. We can just say, be an Ether channel, you're on. Or we could use a link aggregation protocol which can dynamically form an Ether channel. Cisco came up with their own link aggregation protocol. It's called a PAGP, Port Aggregation Protocol, but now there's a standard LACP, Link Aggregation Control Protocol. And let's take a look at how each of these protocols can form an Ether channel. Remember I said that there was an on mode. If we just say that both sides are on, we're not going to be sending any PAGP frames. We just declare that we are an Ether channel. And both sides set to on will cause an Ether channel to form. But if one side is set to on, no other setting other than on will work on the far end of this Ether channel. So on is not going to be compatible with anything else. What about the combination of auto-auto? This is a lot like DTP when we were dynamically setting up a trunk. Remember, if both sides of a trunk were set to dynamic auto, they were both willing to form a trunk, but nobody was initiating the trunk formation. Nobody was sending the DTP frames. Same thing here. If we have this set to auto, both sides are willing to form an Ether channel, but nobody's initiating it. Nobody's sending the PAGP frame saying, hey, let's be an Ether channel. And as a result, auto-auto, that's not going to give us an Ether channel. However, if one side is set to auto and the other side is set to desirable, the desirable side, it will initiate, it will send out those PAGP frames. The other side will see those and say, oh, you want to be a channel? Great, let's form an Ether channel. Again, desirable and on will not work because on will only form an Ether channel if the other side is set to on. We already said that desirable and auto work. What about desirable? Yes, just like in a trunk, both sides send DTP frames and a trunk is formed. Same thing here. If both sides are set to desirable, both sides are sending PAGP frames and an Ether channel will be formed. The industry standard approach is LACP. And again, we could say both sides are on, and that would form a channel, so that would work. And again, on is not compatible with any other setting, so we'll put an X for each of those. And instead of auto and desirable, we have passive and active. The terminology is just a bit different with LACP, but it really works the same. Passive works like auto. Two passive interfaces will not form an Ether channel. Active works like desirable. It will initiate the sending of LACP frames. Passive and active will form an Ether channel. Again, on, not compatible with anything other than on the other side. Passive-active, we said that works. And of course, just like desirable and desirable would bring up an Ether channel, active-active also brings up an Ether channel. Now let's talk from a troubleshooting perspective about some things that might prevent an Ether channel from forming. A really common reason that an Ether channel doesn't form correctly is we have mismatched parameters on each side of the channel. Each port needs to match in terms of duplex and speed. They need to be identical. Maybe things aren't working as expected because after we created the channel, we didn't create a trunk over that channel. After we create the channel, then we can go in, just like we would go into an interface and say, your trunk encapsulation type is .1Q, and we could set the trunking mode to dynamic desirable, something like that, to form a trunk over that channel. Just setting up a channel by itself does not mean that we have a trunk on that channel. And another really common issue people have with Ether channel is they've got a false sense of security. They think they're doing load balancing, but they don't understand how the load balancing algorithm works, as we just discussed, and as a result, they're not getting the performance they anticipated. Now, let's go out to a live interface and see how we can gather some information from an existing Ether channel configuration and see how it's set up. In this topology on screen, we've got an Ether channel set up between switches SW2 and SW3, and let's see how we might gather information if things are not working as anticipated. First, I might want to make sure that a trunk is set up between these switches. Now, this Ether channel does not have to be a trunk, but oftentimes, that's one of the reasons you want to create an Ether channel, is you're going to create a trunk over that Ether channel to carry traffic for multiple VLANs. Let's see if we have a trunk formed on this Ether channel. Let's do a show interfaces trunk command, and we do. Notice the Ether channel's port identifier is P01. That's port channel 1. In fact, we can get more information about that interface. We can do a show interfaces P01. And notice this. Notice the bandwidth it says we have for this interface. These are 100 megabit per second interfaces, but I have two of them bundled together. And as a result, it says that we've got 200,000 kilobits of bandwidth. We can get additional insight into our Ether channel configuration by saying show Ether channel. And this shows our group number is 1. The interface is therefore port channel 1. We've got 2 ports in this channel, and this channel on this particular switch model will support a maximum of 8 ports in a channel, and we can see what protocol we're running. Instead of running the industry standard of LACP, we're running the Cisco proprietary PAGP. And we might also want to see how we're doing the load balancing. That's a big deal when it comes to troubleshooting. To see that, we can say show ether channel load-balance, and it tells us that we're doing source MAC address load balancing. If we want to change that, and I probably would want to change that in the real world, let me show you how we do that. Let's go into global configuration mode, and we can say port-channel load-balance, and some context-sensitive help shows us the options that we saw earlier. I think I'm going to go with source and destination MAC address. It's going to do an exclusive OR with the last 2 bits of the source and destination MAC address. Now, exclusive OR simply means this. It means if the last bit, the 48th bit in the MAC address for each of these devices, the source and the destination, if those last bits are the same, then the exclusive OR would result in a 0 because they're the same. An exclusive OR means that we're only going to get a result of 1 if those bits are different. If the last bit in the MAC address of the source was a 0 and the last bit in the destination MAC address was a 1, they're different. The exclusive OR operation would result in a 1 in that case. And then we would do the same thing for the 47th bit in the MAC address. We're looking at the last 2 bits if we have 4 physical paths. If we had 8 physical paths, then we would look at the last 3 bits because 3 bits can give us 8 different values. Here, let's set the load balancing algorithm to source, destination, MAC. And what we've talked about up till this point is a layer 2 ether channel, but we could have a layer 3 ether channel. Much like you would go into an interface on a multi-layer switch and say no switch port and assign an IP address to make it a routed port, we could do that with our ether channel port. And to make that happen, we would have to say no switch port for the physical interfaces, and we would also say no switch port for the port channel interface. And it's to the port channel interface that we would assign an IP address. There is one extra thing to consider when we're troubleshooting a layer 3 ether channel though, and I wanted you to know about it because it's not really easy to spot. Sometimes it matters in what order you set up your layer 3 ether channel. For example, if we went into our interfaces and we said no switch port, and then we said you guys belong to port channel 1, and that creates the port channel, and then we went into the port channel and said no switch port and assigned an IP address, that might not work. And the reason that might not work is that we should manually create the port channel. We manually create that virtual interface before we assign ports to that port channel interface. To prevent an issue like that from happening, Cisco recommends that if you're setting up a layer 3 ether channel, statically create the port channel first. For example, you could say interface port channel 2. And then you could say no switch port. And after you've done that, after you've created this virtual interface, then you could go to your physical interfaces and say no switch port and say that they belong to this port channel interface. So order of operations can be a big deal when we're working with a layer 3 ether channel.